Okay, this is our short lecture on green functions and delta functions. And where we, in this class, got started on this is suppose that we have our equation for the electric field. The magnetic one is similar. And this is our standard wave equation up to here. It was equal to 0, but suppose it's not equal to 0, suppose we have the source term. And I'll just write that as capital S. I'll put the serifs on it so we know it's capital. And how do we solve this? Well, the first thing we note is it is a linear equation. And so that means that we can solve for point sources and then add the solutions. Remember, if it's a solution, one is a solution, another is a solution, the sum is a solution. So you can add the solutions. And of course, the point by point makes use of the fact that a delta function is a point source. And let's take that a little bit further by defining what we mean by a green function. We'll take some linear operator we'll call L. Okay, so this, think of as linear operator such as, for example, del squared minus u epsilon partial t squared. That can be L. It operates on some function g. That's going to be our green function. And we're going to set it equal to just some point source. Now, to see what we mean when we say add the solutions, let's add the solutions. So we'll take the integral of both sides, integral of L, G, and we'll make this G of x prime, S x prime, dx prime. And this can be in one dimension, this can be in many dimensions, it doesn't really matter. Dx prime can be dx, x, y, z. These can be like vectors, so dx vector prime is a volume integral in that case. And this is equal to the other side, right, which is the integral of delta. Since this is delta, we're putting the x and x prime here, x minus x prime, s x prime dx prime. And we can take the linear operator out if it is linear and integrable and continuous. All these nice things that we're happy about physics stuff because always find that not always linear, but at least in the other cases, physical reality is continuous, integrable usually. And so then you end up moving that out, get L, and the integral of g x prime source x prime dx prime, which is a function of x now, that's equal to this. Well, the derivative, we can use the delta function to solve that. And this is our source. So this must be our solution. Sorry, and I'm going to put in parentheses here a particular solution. Now, when we thinking about boundary conditions, then we take our full solution, which is equal to some function f of r is equal to the convolution, which is the particular solution, plus a capital F, which is our homogeneous solution. So that simply means LF is equal to 0. Homogeneous solutions, as in other differential equations you've probably seen before, are required to so you can satisfy boundary conditions, right? That's sort of the job of these. They give you enough freedom, the homogeneous solutions give you enough freedom that you can match the boundary conditions while still solving this. Right? So that's expected that that's going to have to show up in there at some point. Okay, so then let's keep our heads about us and write down Green's identity, which is going to help us do these boundary conditions. For F and G. Now I was hoping that that would fix itself while I was writing. No such luck. There we are. Maybe it wants to have the point up. That seems to be its favorite. So if I write down Green's identity, it goes something like this. F of R is equal to the integral over the volume of the problem of G R R prime S of R prime D cubed R prime, we're in 3 dimensions, plus 1 over 4 pi. This is the convolution part. This is the surface term. So this is the surface of the problem. Let me shift this over so I can write the whole surface term, which is big. G R R prime partial F R prime partial N prime minus F R prime partial G R R prime partial N prime dA prime. And so if you want to think about this, this is G gradient of F or dot gradient of F dot N prime dA prime. And this here is F dot gradient of G dot N prime dA prime. The reason why I put an N on it is that's the surface normal that really comes up here. And the surface is what's being integrated on, so that I have primes on that, like the A prime. So this then is Green's identity. And you use it different ways. This is what we're interested in getting. This is sort of our solution. This is our full solution, right? Full solution. This sort of gets it. This is our inside our convolution, sort of inside part. And this part here is the surface, and the surface is where we have the boundary conditions. So if there's really two types of boundary conditions, there's the Dirichlet and Dirichlet boundary condition means that f of r prime is given on the boundary. And of course, that means that we know the second term over here of capital F. And so we choose G, which is the first term that we don't know. So it is 0 on the boundary. And then you don't need the first term. So you don't need to calculate that. If you have Neumann boundary conditions, it means that partial f r prime partial n prime is specified. Boundary. And that means we know the first term over here. And so we want to get rid of the second term. And so you can take set partial g partial n is equal to 0. So, you know, g equals 0 isn't good, but it can be a constant. Across the boundary, and then you can actually have a solution. If you want more information on this, a lot more detail, you go to Jackson, Classical Electromagnetics. And if you have the red edition, I can tell you exactly where it is. The different colors is a green, a red, and a blue, depending on the age. In the red edition, it's in chapter 1, section 1.10. It's pretty close to that in the other editions. Okay, so that kind of gives us an idea of where we're starting from. Now, what I'd like to do is talk a little bit about delta functions. Because there are some idiosyncrasies of those you probably ought to know about and will come in useful E&M and other optics, other places, careers. I just more or less used one there blithely without really thinking about it. But if we integrate from minus epsilon to epsilon of delta of x dx, we get 1. And so it's very narrow. If you integrate from minus infinity to infinity, delta of x, it's also equal to 1. So it's 0 pretty much everywhere. Take epsilon as small as you want. If you want to visualize that, you can take a bunch of Gaussians where you start wide and you start making a Gaussian narrower. And so you can say it's the limit as sigma approaches 0 of normalized Gaussians. And that's going to be delta of x. Another way you can do it is you can take blocks. Blocks that have a width here, w over 2, and a height of 1 over w. And so the area equals w times 1 over w, or 1. It's normalized, and then the limit as w approaches 0 of the normalized block. Sorry about that. Is equal to the delta function again. So you don't know what the shape of the thing is. In some sense, it doesn't even matter what the shape of it is. You can define it as a limit of several different things. And then that can hopefully make you happy. Now, as far as use, integral minus infinity to infinity of f of y delta of y is equal to f of 0. F is a test function. That has to satisfy certain integrability. And a few other things that I won't get into here. And that is useful if I have something more complicated, like I just wrote down. I have f of y delta of x minus y dy. Then I do a change of variables, right? C is equal to x minus y. dz is equal to, in this case, minus dy. And I can, what is y? Y is equal to c minus x. No, x minus c. Because, yeah. And if I do that, then I have something that looks again like this one, but with an x minus z there. I'm setting the z equal to 0, and so I get a f of x out of that. And so that's allows us to move it around. With the point around. And then something here that might scare you, might make you happy. The integral minus infinity to infinity of f of x delta 2x dx. We're going to proceed like we did above. we're going to set y equal to x. That means dy is equal to 2 dx. We plug that in, we have the integral minus infinity to infinity of f y over 2 delta y over 2 dy. And if we evaluate that in the normal way, we get f of 0 over 2. So if you just said, oh, I swear that thing equal to 0, write f of 0, wrong. It's scale. Yeah, this is like an axis scale. And we see that things aren't quite as trivial as you thought. And so now brings us to the natural question of what if we have this? Integral minus infinity to infinity f y delta function of g of y dy. And we now know our answer. X is equal to g of y. Dx is equal to g prime of y dy. Where here I'm using the standard notation that g prime of y equal to dg dy. The prime is the derivative with respect to the only variable that you have. And so the issue here is we're going to get a signal whenever g of y is equal to 0. So we get get a delta function point wherever g of y equals 0. So if I just take a plot here of g as a function of y, and remember g is really our x in our new variable here. Suppose it looks like this. Suppose it goes boing, boing, wiggles up here, and then it comes crashing down again. Well, we're going to have a y1, y2, y3, y4. All that are going to have to be included. So we're going to have a sum over, let's call it I. And this is where y sub g y sub I equals 0. Wherever that happens, it's going to be a sum. Now, we then can write this as the integral from, okay, we need to know what these points are, and we're going to go a little bit before and after, kind of like we did up there with the epsilons. So it's g inverse of xi minus epsilon, g inverse of xi plus epsilon. That's the y's, right? So we're going to take epsilon to either side of the 0, integrate across that. That way we're separating them apart. And we don't have to double integrate. And our function here is function of y, and y is equal to the g inverse of x of I. And delta of x sub I, that's nice, simple thing we wanted. And as above, we find that if this is here, we have to put g prime y in the bottom. The first derivative of y sub I. D integrating over dx. Now that looks to you pretty good, huh? But wait a minute. We look at this point here, we find that this one's at the bottom, and that one's at the top of the integral. And so that's okay. And the integral is positive and the slope is positive. So integral is plus slope plus, you get a plus. On this one here, you get this at the top and this at the bottom. So the integral is backwards. That means the integral is minus, and the slope is also minus. So minus times minus equals plus. And we said, oh, this shouldn't be a minus here with g prime negative, it should be plus. We need to put an absolute value. Over here, it's going up. Again, integral's in the right direction. Slope is in the right direction. It plus works. Down here, it's going minus, just like this one. Integral is backwards, the slope is negative. We actually need this absolute value here. That's the detail that you can't kind of throw out in the dishwater, as it were. And so if I just want to summarize here, you can write delta of g of y is equal to the sum over I, where g of y sub I equals 0, of delta of y minus y sub I over the absolute value of g prime of y sub I. And if I plug that into that, then technically, I guess this up here needed to be x minus x sub I. And that, through our shifting one, is just visible up here. It gives you the f at the right place. Okay, so that is a start on the delta functions. Let me use this to give an example or two. So we had it before, delta of 2x, now g of g of y is equal to 2x, g prime of y is equal to 2. And so this had better equal to delta of x over 2. And that's what we found before. And let's do one more. What is delta of sine of y? That's equal to the sum of m equals 0 plus or minus 1 plus or minus 2 of delta of y minus m pi, right? This is 0, 0. It's 0 pi in either direction, both directions from that. And we have to divide by the slope. The slope in absolute value is cosine of m pi. That's what it's going to be, or some 2 pi equivalent to that. Of course, all those are 1. And so this is equal to sum m and is an element of an integer of delta y minus n pi. So something as nice as delta the sine of y becomes an infinite number of delta functions equally spaced out by n pi. That might be good for something, who knows? As far as units go, you watched my coordinate systems things, you realize, okay, units, something we always pay attention to. The integral of f of y delta of y dy is equal to f of 0. Well, it's pretty obvious to see that this and this have the same units. And it actually doesn't even matter what those units are, always going to be the same. So that means these need to cancel units. So the delta of y has units 1 over whatever the units of y are. Typically that's going to be 1 over length, if we're talking about a normal axis. But it can really be 1 over whatever it is that those units of y are on the inside. So delta functions have units. What about a 3D delta function? Remember, we were using a 3D delta function. Well, the easiest 3D delta function to think of is delta cubed r is equal to delta of x, delta of y, delta of z. Of course, the units of this is 1 over length, 1 over length, 1 over length. So the units of this thing here have to 1 over length cubed. In other words, it's good for a volume integral. It'll take care of the units for you. So the next step is to get a formula for the 3D delta function in spherical coordinates. So if we go back to our equation, we had del squared g minus 1 over c squared partial t squared g is equal to minus 4 pi delta cubed r and t. And this minus 4 pi to put out in front here, that's convention. You'll see why it's convention in a minute. And we want a spherical coordinates formula. Largely because we already know it in rectilinear, and we're more interested in spherical than others. So let's consider V is equal to 1 over r squared r hat. So what does that mean? That means that if we talk the origin here, it's pointed away, and it goes to 1 over r squared. So it gets shorter as we go further in any direction. Spherically symmetric. So the divergence of V is partial Vx, partial x, plus partial y plus partial z, partial z. which we need to convert to spherical coordinates. And note that the no theta or phi dependence. So we only need the partial r terms. Again, if you go to my lecture on converting, we need the divergence in spherical. You can go and look that up. And what you find is del dot v is equal to 1 over r squared partial r squared v sub r. V sub r, of course, is 1 over r squared, which is equal to 1/2 we're doing the product rule here. Oh no, actually don't need to do the product rule, right? That goes away there. So we get 1 over r squared times partial r of 1, which is 0. So you say, well, that didn't seem to give me anything. But it gives me 0 everywhere except, let's think about this. If we integrate this divergence over some volume, we can apply Stokes, the divergence theorem here. And then we get across, say, this is about an inside sphere. This is sphere surface at radius r. And good luck, pen, it doesn't go out of focus. This is b dot dA, which is the integral on that surface. I chose it to be at r hat dot r squared sine theta d theta d phi r hat. And if you look closely at this, there's an r hat that goes with the volume element. There's an r hat over here. R hat dot r hat is equal to 1. And so this is equal to integral theta equals 0 to pi, phi equals 0 to 2 pi of sine theta d theta d phi, and that happens to be equal to 4 pi. Now, if you look back, you say this argument here fails at r equals 0. So all of this at 4 pi must be from the origin. And so I can summarize this integral of del dot r hat over r squared divided by 4 pi dv is equal to 1 due to the origin, right? Del dot v is 0 everywhere except where it fails. If I integrate over the volume, I get 4 pi. So the integral of this thing is to the origin. or delta cubed of r in spherical coordinates is equal to 1 over 4 pi del dot r hat over r squared is equal to minus 1 over 4 pi Laplacian of 1 over r. Since the gradient of 1 over r is equal to minus r hat over r squared. If you're interested in more interesting integrals, okay, make a note here, other r integrals. There are derivatives. If you take the gradient, here's the divergence of r to the n times r hat, you get it to be n plus 2 r to the n minus 1, except for r equal to minus 2, except n equal minus 2, in which case you get the delta function. And so that's the divergence of interest. You actually can write that down. And other things you should know is del cross r equals 0, a dot gradient of r is equal to a. Now to make something complicated, if it's simple, you can do it that way. R hat dot gradient of r hat is equal to 0. And the curl of r to the n r hat, right? This is divergence. You take the curl of that, you in fact find it is 0. So that function then is has a divergence with no curl. It's irrotational. R to the n r hat is irrotational. Kind of expect that, doesn't have any angles in it. The other thing to note here is for delta in cylindrical, polar, you're going to use the Stokes theorem. And that's going to allow you to back out what it is. Okay, so we went back to our equation. We found out now what the delta function in fact looks like, and it turned out to be rather simple. So what we're going to do now, try not to lose our focus. We did, so let's get it back. Okay, so we have it back. So I'll write down our equation. yet again. And so our Green's function, we just wrote down, is equal to 1 over r prime delta function t prime minus r prime over c, where we have stuffed in here. So this is actually the solution you get here. So causality and the finite speed of light are built into the Maxwell's equations. And the reason why I say that, of course, is because that's what you get as a solution for the Maxwell's equation. It has that retarded time. Right, this is retarded time. It means that where you are at a certain time is delayed by the propagation time, r over c. So let's actually solve this equation here. We add by integration. So our function f is equal to the integral of source r prime t prime g r minus r prime t minus t prime dv prime dt. That's the convolution. And plugging in, it's 1 over 4 pi, the integral of the source, where it is, where it has been. So the time is just going to be delayed. That's what our delta function tells us. Over, it's where it is, and we have a delayed time, and the normalizing is the r prime minus r dv prime. So you're integrating over your charge distribution, which is primed here, as a location, matters where the source is. Your time dependence is driven by the delayed time. Your distance away from it is where you are minus, doesn't matter which way it is, it's an absolute values. Where you are minus the source position, it's how far. It took time to go there. There it gets your time dependent function for your electric field. So to get some insights into this, let's take the special case where r's, r primes, are all much less than r. So I have some localized r primes. So charges. And my observer is over here. And that's r. And so in this case, r is much bigger than r prime. I can just put r in and factor it out. So my f is equal to 1 over 4 pi r. the integral of the source r prime t minus r over c. I can drop the r prime there as well, dv prime. And if I take a simple harmonic source, that looks something like a naught over omega sine omega t. And then my solution E is equal to F is equal to a naught over 4 pi r cosine of omega t minus omega over c r equals a naught over 4 pi r cosine omega t minus kr. Or sometimes you'll find this as, or to deal with phase, easier. You'll write it as a naught over 4 pi r e to the I omega t minus kr, which is of course a spherical wave. Now, the important thing to note here is this kr term here. We're used to this. Waves. But now we see it comes from retarded time. And that without retarded time, there's no radiation. That's actually fairly easy to see. If the speed of light was infinite, then news would get out infinitely quickly. And what's the propagation? Happens infinitely fast. The real propagation to worry about in that case, right? It's just there. So because of that, we just ignore it. So what I've shown you is for the wave equation with sources, we have a green function. I hope you've learned along the way of getting there some insights. It gives us a spherical wave. I know where that comes from. You've seen that that's the retarded time function. And hopefully you've got some interesting properties of delta functions that you can now use for your enjoyment. That's the end of our little escapade here.